Hi everybody, welcome back to Edu-Malanga. Today we will continue with topic 1, which is patterns, sequences and series. We'll be looking at a new lesson under the topic, and that's geometric sequences. We're going to start by deriving our own geometric sequence using variables. Then we're going to define the variables and make sure that we understand them properly. After that, we will come up with a word definition of a geometric sequence. Then we will end the video tutorial by deriving the general term of a geometric sequence. Let's begin then with the derivation of our own geometric sequence using the variables that are important in the topic. If we recall from the last tutorial video we did under topic 1, patterns, sequences and series, we describe how every sequence will always have a starting term, and we said that the first term of your sequence, which is known as term 1, denoted by the abbreviation T1, is very important because it tells you where your sequence starts. For example, if we look at odd positive numbers, that sequence would start with 1, go to 3, 5, and so on. It's always important when working with any type of sequence to define the starting term of that sequence. The variable that we generally use to denote the start of the sequence is A. To derive the next term, we need to be clear what kind of sequence we're looking at, and we're looking at geometric sequences. So what do you do to term 1 when you are looking at geometric sequences in order to derive term 2? Term 2, let's start by writing. In order to derive term 2, we're going to have to do something to this term. For geometric sequences, that thing that we do with the term is we multiply it by something. So what we'll do is we need to use term 1 as it is. So we take the A, and then we need to multiply by something. And what we multiply by is called the common ratio. It is denoted using the variable R. The common ratio is referred to as common because it is what you multiply the current term that you are looking at in order to come up with the next term. You will always multiply with that ratio to derive the next term, hence the words common ratio. Let's derive term 3 then, having understood that. For term 3, we're going to take term 2 as it is, so let's rewrite it, A times R, and we're going to multiply it again by the common ratio, times R, and we now have term 3 of the sequence that we're deriving. To make sure that we are completely understanding this, let's derive term 4. Again, we're going to use term 3 as it is, A times R times R, and because we're deriving the next term of a geometric sequence, we're going to multiply by R, and what we have now is the fourth term of this geometric sequence that we're deriving. So what are the two variables that we've looked at? We've got the variable A and we've got the variable R. Let's define them. A is the first term or the initial term of the sequence. It's always important to define the first term because it tells you where the sequence starts. And R is the common ratio. The common ratio is what you multiply the current term you are looking at with in order to derive the next term of the sequence. Now that we've understood the variables, how could we use words to define a geometric sequence? A geometric sequence occurs when you have multiplication of an initial or a first term. The first term, we denoted it with the variable A by a common ratio, which we denoted using the variable R. So that is how we would use words to define a geometric sequence. There's three things to note in this definition, and that's multiplication, that's the first term A, and that's the common ratio R. These are the things to remember when working with geometric sequences. In this derivation of our sequence, we went as far as term 4. But what if somebody were to ask you, what is term 80 of this sequence? Would you continue on and do term 5, term 6, term 7? No, that would be very tedious. The whole reason we're looking at patterns, sequences, and series is so that we can come up with simplified equations for denoting patterns, sequences, or series. So what we use to do that for any kind of pattern, sequence, or series is the general term. The general term of a sequence is used to derive any of the terms that belong in the sequence. So for example, term 1, you can get it from the general term 2, or term 80. And to derive the general term, we're going to introduce one last variable that will be relevant in this topic, and that is the variable n for term number. If we look at these terms, n is represented by 1 because we're looking at term number 1, by 2 because we're looking at number 2. So that's what n represents, the term number. There's some important restrictions to note about n, and we can read them again out very clearly when looking at the sequence that we derived ourselves. The first thing we'll notice is that it starts from 1, 2, it grows from there, so it looks like it's always positive. So n will always be positive. And if we look again, we'll realize that we're also only using whole numbers. All of these numbers are whole. None of them are fractioned. We don't have term 2.5 or 2.8. So n will always be a positive whole number. That is important to remember about n, because if you're ever solving problems pertaining to a particular sequence, if you find n that is a fractioned number, then you know that that term does not belong in the sequence. Let's get then into how the general term of the geometric sequence looks. To understand the general term, we're going to have to use the sequence that we've derived ourselves. We'll begin by simplifying the terms that we have come up with for this sequence, and what we're going to look for is patterns. We're going to look for patterns that are very obvious in the relationships between A and R, so we can come up with an equation that has Tn is A and whatever happens to R. A always appears in all the terms of the sequence. So far, it's appearing in term 4 all the way to term 1, so the general term for geometric sequences will therefore always have A as a part of it. And now we need to understand the relationship between n, which is the variable that we introduced, and r, which is the common ratio of our geometric sequence. To do this, first we'll simplify so that the relationship becomes clearer. Term 1 cannot be simplified further because you only have one term, which is A, and term 2 can also not be simplified further because you have two terms, but none of them are alike. You have A and R. Term 3 can be simplified though, because you have two like terms, which is two R's. So then term 3 can be simplified into A times R is equal to R squared. Term 4 can also be simplified as well. You've got three like terms this time. So you have A times R, which is R to the power of 3. We've now simplified the terms of the geometric sequence that we derived. Let's look for a pattern now between what we've called Tn and the power of R. Let's start at the bottom and work our way to the top. So, for term number 4, n becomes 4, and something must happen, and the power of R is 3. How would you get the number 3 when you start with 4? You can do this by subtracting 1. Yes, and then you get 3. Let's see if this is true for term 3. In term 3, you start with n is equal to 3. So 3, and if you say minus 1, you get the power, which is 2. Correct. Oh, that looks like a pattern. Let's look at term 2. You have 2, and you subtract 1. Yes, and you get the power, which is of R, the power of R, which is equal to 1. Nice. And let's do the last test for term 1. You have 1 minus 1, which is equal to 0. We don't see R at all. Here's a mathematics fun fact that you may not know. Anything to the power of 0. So, for example, in our sequence, we're using R. R to the power of 0 is equal to 1. In mathematics, anything. It could be A, it could be a number like 8 or 16. If it's to the power 0, it's equal to 1. So now that we've derived a pattern, let's use n. Essentially, you have n minus 1, and then that gives you the power of r. So if we come back to our general term, we get a times r to the power of n minus 1. This is the general term of a geometric sequence. You can use the general term to derive any term that belongs in the sequence, term 1 all the way to term 1000. This is the end of this tutorial video. I hope I have explained well and you understand the topic. Join us in the next video where we will do examples on geometric sequences.